Alright, here we go. Assignment 8, pick up sticks. So basically this program, we're going to simulate this game called pick up sticks. If you remember this game from when you were a kid, if you don't remember this game, the way it works is you try to pick up sticks one by one without, I guess, hitting other sticks when you're picking up sticks. I guess that's probably the best way to think about this. And we can think of each stick as being like a node in this graph, and in the edges are going to be really dependencies. So let's say if so basically we label each stick with a number 1 through n, and let's say if stick 3 is on top of stick 4, then in the graph 3 will be connected to 4 with a directed edge like that. So the idea is the edges are going to be our dependencies, like which sticks are on top of which ones, so we know what order they can be sort of removed. That's basically the concept behind how we're going to store this into a graph. So this first paragraph over here is sort of, explains the whole problem, and we're going to have to use depth first search in this program a few times. So the first use of depth first search is going to be to detect a cycle in your graph. Now I'm going to link a few other videos to the assignment as well that goes over those concepts. So that way, just since it's already kind of out there, I figured just to save myself a little time, I'll just link that there. But anyway, I'm going to go over sort of the concepts here. So at least talk about it a little bit. But anyway, to do this depth first search, well, we're going to first need to have our graph. But anyway, we have to do a topological sort of this graph. That's going to give us the output. Topological sort really is just sort of an ordering of the node IDs or nodes in a way where we have our dependencies set up. So I'll talk about that a little bit here as well, but I'm going to post a video that also goes over this topological sort. And to do a topological sort, a stack is needed, which in that video that I'm going to link will explain it, and a stack will be needed. So guess what? You're going to create a stack class. This is going to be a stack that's going to be using the array implementation. The reason why is because for assignment 1, I believe, you guys used a linked list implementation of a stack, and we don't want you to reuse that because that would make the whole process less fun, because now you would do less work. So to do more work is always better, right? So we're going to implement our own custom stack. Now, I'm not going to go over every single part of it. I would imagine you guys would understand how to do this. But anyway, let's go ahead and just talk about this quickly over here. So anyway, well, we have our type star stack. So of course, it's going to be a templated stack. And this is going to be basically a pointer. It's going to be a dynamic array. Size is going to tell you what's the max number of elements that can be stored in this array. And the stack top sort of variable here, that's going to denote the top element of the stack. So as you push elements on there, you assign the elements into this index, into stack top index, right? And you increment stack top by 1. And if stack top equals size, that means your stack is full, so you have to resize basically. So the push operator basically does that. Just you take this element you're passing in, you assign it to the stack top position of the array, you resize if necessary, and that's about it. The pop operation, well, that's if a stack is not empty, it's going to return that top element without, and it's going to remove that top element as well. So figure out a way how to do that. So remember, we have this stack top variable that maintains, the stack top. So maybe decrementing it by 1 would be a good idea. So giving a little bit of a clue here. The peak function, well, that's basically returns that top element without removing it if the stack is not empty. So if it is empty, remember, return some default values. Remember, return type with the 2 parentheses, just like that. And then is empty returns true if the stack is empty and false otherwise. So how do we know if a stack is empty? Well, if the stack top equals 0 or something along that nature, then we know we had no elements pushed on our stack. If that's basically it. So you could set the initial value for stack top to be 0 or -1, depending on how you want to do this. And then of course the constructor here, that's going to just basically create a stack size of 10 allocates the array to the stack pointer, and it will set the stack top to -1 or 0 depending on how you want to do this. Some people like to assign first, then increment, or increment then assign. It does increment that stack top and assign, but it's up to you how you do that. Copy constructor, assign operator, destructor. I'm not going to go over these because I think since we're using a simple array, I can't imagine this being anything complicated there. So that's basically it. Have your stack class. That's not really much of a problem. And here's a description of all that there, so you can read through that. I don't think this will be a problem. And here we go. Vertex. Look at this. We got a struct node inside of Vertex. My goodness, we actually have another class defined within Vertex. Then we have all the vertex members, or the vertices members, but I'll call it vertexes only because this is a class, but obviously I think vertexes is not proper to say, although I think you can, but I was taught not to say it like that, so I'm going to say vertices, but I'm going to say vertexes now because, you know, it's the class name, so, you know, anyway. So pretty much, this is going to be the magic of your graph. So you're going to store a graph using a vertex. So what is an iterator? Well, the iterator is basically going to be sort of a beefed up pointer. So it's a pointer, but it's kind of wrapped around with the class. And notice that we have this member plus plus star, and we have this node star current. So an iterator basically is just an object that contains a pointer inside, and that pointer is going to point to a linked list. So these functions, for the most part, are going to be one-liners. I'm not even joking. They're all one-liners. They're really easy. It's not easy to see what this does automatically, but I'm going to show some examples to kind of help you understand how iterator works. And then the videos on topological sort and detecting a cycle in the graph, I'll just give you those videos from a YouTube video just from somewhere else. But I'm just going to go over like really how to handle this class and how to use it in main. Then we have our vertex class. So basically this vertex is going to be a linked list, and it's going to store all of the sort of neighbors of a particular node, just like the example I did earlier, but that one used like a straight up, you know, node star star. Here we're going to do the same thing, but we're going to overcomplicate this a little bit, just because, you know, we have to overcomplicate everything, because without that, you know, we can't really, you know, do anything. We have to make sure things are as complicated as possible. So here's all the explanations, but I'm going to just talk about this instead, you know, in layman's terms. You can read this on your own, but I'm going to just kind of talk about this because it'll be more helpful than having you read through all this. So I'm going to go ahead and pull up the whiteboard app, and I'll just kind of explain and draw some stuff out here to get an idea of how to think about this. I'm going to move this to the different side over here to a different screen so I can refer to that. But I'm going to just basically just go over this here. So in your main, you want to store a graph. So let me go ahead and actually pull up the input file, and I'll just kind of show you how to think about this. So in this program, so in the handout that you're going to read, you can see that you can be given an input file. I'm going to just open this one up right over here. This one's actually too simple, so I'll just go and go over this one. Yeah, this one's a little bit nice. This is a nicer example. So here's going to be the input file given to you for pickup sticks. So this 5 tells you how many nodes you're going to have, and then this 10 tells you how many edges you're going to have. So 10 here, I'm going to make a bet there's 10 lines here. And each of these is going to be just an edge, which means 1 goes to 3, 1 goes to 2, 2 goes to 3, 1 goes to 4. So we can see very easily how we can construct this this sort of adjacency list, but we're going to do this in an overcomplicated, convoluted sort of way. So I'm going to go ahead and pull up the whiteboard again. So I'm going to try to just mimic this and move this over here. But of course, you can, you know, pull up the file as well. But I'm going to go ahead and just do this. So the first to read is 5, which means there's going to be 5 sort of nodes. So what I did in my program, so we basically just have this vertex class. Okay, so I just create vertex, and the type will be int. So since we're storing integers in this, I'm just going to give you that, and I'm going to call this, I'm going to call it sticks, I guess. And it's going to be a dynamic array, because we don't know what the size of the graph will be until we start reading stuff from a file. So after that, I mean, open input file stream, reading the first numbers. So I'm gonna, create me a variable called vertices. Obviously, you have to call it vertices. That's the proper way of doing that. I'm not going to say vertexes, although that could be proper as well, but I don't want to use that word just because. Anyway, once you read in from our file, remember, our file contains two things. Oh, that disappeared suddenly. Okay. So anyway, we're going to basically read in that 5 first. So you have 5 vertices, obviously. And they're labeled 1 through 5. So I'm going to actually do the following instead. So what I'm going to do is when I create my file over here, I read my vertices amount, and I create my array by saying sticks equals new vertex int, and I actually use vertices plus 1. I guess the purpose behind doing it like that is just so basically elements 1 through n will be used, and element 0 is not going to be. It's going to be kind of a throwaway. But I mean, I could do it like where I just say vertices and have to keep on subtracting 1 from the input, but I don't want to do all that. So this is kind of a little bit easier. So what happens over here is the following. So what this does is it creates the following structure. Let's say we have the one file where we had 5 vertices. So what happens here is I'm going to use this ruler because it will look a little better, I think. Hopefully I don't mess this up right now. But I'm going to go ahead and create this over here. So basically each element, so let me just sort of draw this out, and then we can kind of talk about this afterwards. So each element of, how should I say, this vertices array is going to be its own linked list. So in that vertex class, if you notice, we have this node star neighbors inside of it. That's going to be your linked list. So that's how you can visualize it. I could talk about this some more next week as well in case I have time, but I'm doing this just in case I run out of time during the week. So anyway, all right. I like this. I should have used this before too. I should have done this a long time ago using this ruler instead, but I'm still kind of a noob to using this. I should put up a little here. I'm a little bit of a noob to using this app, but I'll get more practice probably as we go. I mean, in the future I'll get more practice with this. So let's say we had 5, so I'm going to create a 6 array thing here. So let me just wow, this is very not even, but that's alright though. It's gonna be okay. It's gonna be a little bit lopsided. I'm sorry about that, but at least it doesn't look that good because this is very weird. 1, 2, 3, 4, 5, 6. Well, you know what? That's how it's gonna be, I guess. Oh well. So we're gonna have this what's it called? Sticks, I believe. Okay, we're gonna have our sticks pointer points to this, and then we'll have our array indices here. So elements 1 through 5 will actually be used. Element 0 will be kind of a throwaway, but this is kind of a nice way to implement this. So each of these elements here, I'm going to try to write this here if I can. So each of these is going to have its own neighbors pointer. I know it's kind of hard to read that, but you can kind of imagine I tried to write the word neighbors. Yeah, it's really hard to read that, but it's okay. You can visualize. It's trying to spell the word neighbors out. Okay, so basically here, when we read from our file, which I'm going to pull up the PDF over here. There it is. Oops, it's not showing up on this screen. There it is. Okay, so we have a function in our vertex class called, let me see, where is it? So you can find it here somewhere. Add edge. There we go. This is going to add an edge into our linked list. So add edge is usually pass in some integer in here. So let me go ahead and just show it here on the board how we would do this. So for every edge in our file, it's an ordered pair. It's not ordered pair, but it's two elements. Remember, so let me just go ahead and pull up the file over here. It's like this. See, 1 goes to 3, 1 goes to 2. So every line contains two things. So it's kind of like a from and a to. So from to 2, I think. So we can use variables from and to like that. And read into 1 to 3, and then 1 goes to 3. So let's go ahead and see how we would do that. Well, we're going to have maybe variables int, I guess, from and to. So after we read in from and to in that file, what I would do is I would just say, well, sticks and then from dot add edge 2. That's how we use the vertex class. So because since sticks is an array of vertex objects, I have to first access an element and then call its add edge function to assign or add in, how do you say, add in an edge into this. Let's say we had 1 and 3 was first, right? What happened is we go to index 1 of sticks, and then it's going to allocate a node that contains 3, and this neighbors will point to it. Now in our file, let me do this here. So in our file, we actually had 1 go to, let me make sure I get the right file here. We had 1 goes to 2 as well. Okay, so next we read in 1 and 2. So you read in from and to be 1 and 2 this time. So then what would happen is, well, I would insert another node here. So I guess the better way of doing this is do a front insert because it is more efficient to do a front insert. So neighbors, that pointer is going to be ahead of that linked list. So I would just go ahead and do a front insert, which I would basically just add a new node to the front over here. And then 3 over there, like that. So you can see it's kind of the same structure, just over convoluted, but the same idea we're going to be doing. Is we're using all this weird sort of vertex stuff and all that to do this. So anyway, that's how we create this. So we're going to basically build this up. And then how do we traverse all the elements? So basically, sticks, 1, sticks index 2 and 3 and all that gives you the neighbors of each node. So how do I traverse this linked list? Well, the iterator is going to be used for that. So what I would do to create iterator, I would have to say vertex int edge iterator, and I'll call it IT. So IT is going to be an object that contains a current pointer inside of it. And that current pointer is going to point to a node in this structure. Any node is going to point to, essentially. So how do I make it point to like this node, for example? Well, we have another function in our vertex class called begin. So if I were to say IT equals sticks, I'll just say 1 dot begin. This begin function is going to return an iterator object whose current field is going to be equal to sticks1's neighbors pointer. So essentially what's going to end up happening at the end of the day is we're going to have this IT object over here, and inside of it, it has this current pointer. And it's going to essentially point to this node. Because when I say sticks1 dot begin, it returns the iterator that points to this node, and it's going to be assigned to IT's current. So in that function begin, you're going to create some iterator object inside of it, set its current equal to neighbors, and then return that object. And then in main, IT is going to receive that iterator object, essentially. So then what happens is, well, how do I access something? How do I return the actual element? So I want to be able to like maybe retrieve this 2 out of this. Well, you have this star operator for the iterator class. So if I were to say something like cout star it, in this class iterator, you have to overload the star operator. And a star operator simply, it just returns that item field. So current points to a node, so you have to have current arrow on the item field and returns that. So because current points to a node, so use the current arrow operator and access that item field, that node, and that's how you access and retrieve that actual index. Now if I want to move to the next element, well, you have to overload a plus plus operator, which is very simple. All that operator has to do internally is just basically reassign current to point to the next node in the linked list. How do we do that? Well, maybe current equals current arrow link. That could be a good way of doing this. But IT++ at the end of the day is going to update its current variable inside of IT. It's going to move current over to the next node. So in current, so IT++ is going to basically update IT's current pointer to then point to the next node in this linked list. So that's kind of a little shortcut, or a little not shortcut, but a little crash course into this. So we're going to have a loop basically that will, set IT to point to the first element. We can use star IT to retrieve that value or that element in that node, IT++ to move, and we can also have the loop, stop. So basically, if IT does at some point equal sticks 1 dot end, so this end function for the vertex class returns an iterator whose current equals null. So if IT, this iterator, equals the iterator that points to the end, which is going to be a null, then you want to stop looping. That's how you loop through all the neighbors of any particular vertex. So I could, of course, explain some more during class or in office hours if needed, but this is basically how you traverse it and all that. And of course, if you want to deallocate this entire structure over here, well, you have to write the destructor for the vertex class. And destructor is basically deallocates a linked list. So all you have to do, so for every single, so in the destructor function for the vertex class is a simple linked list destruction. So neighbors is going to point to a linked list. You do a bunch of head removals, right? But you have to use, you can't use like a pop function because you don't have that here, so you have to manually do a bunch of head removals. But the way to deallocate this entire thing is just simply say delete sticks. It's going to call each object's destructor, and it'll destroy the entire thing. So that's all you have to do, really. So I guess that's pretty much it. Hopefully this video did help you, but of course, if you have any questions, let me know. I will link also the algorithms for doing topological sort and cycle detections as well to the handout. But other than that, though, that's it. So I guess bye-bye for now.